Good afternoon. Okay, good afternoon. Good afternoon. So we had discussed some of the basic definitions of basis, dimension, and okay, basis and dimension in last class. So let us recall that. Okay, the definitions, basic definitions. Let me just quickly recall those things. Okay, so first we have defined the spanning set. Um,
Sir,
Sir, your
screen is
screen
not
is not
visible.
visible.
okay, okay, just a minute. Is it okay now?
Yes, sir.
Is it okay? Oh, fine, fine. Okay.
Yes, sir.
So I just want to recall the basis and as well as, yeah, fine. So the basis and then the spanning set. The spanning set definition, okay. Yesterday we had discussed. Okay, let me go back to that. Basis definition. So spanning set to that. Okay. If something is suppose I want to say that W is a subspace which is spanned by a set S. That means that the set of all possible linear combination of the vectors in S. That is what we had seen earlier. Okay. So examples we had given that S is nothing but an upper triangular matrix union of lower triangular matrices, and then we had taken any matrix. Okay, any matrix in M2 by 2, that A B C D, and we had seen that A B C D can be expressed as A times of 1 0 0 0 plus B times of 0 1 0 0 plus C times of 0 0 1 0 plus D times of 0 0 0 1. So this matrix can be expressed as linear combination of the vectors in S. So therefore, the given S is a spanning set. That is what we had seen. Okay. So now we want to discuss this S is a basis. So if I want to say S is a basis, then it should be having two properties. One is that it should be linearly independent set. That is what we had given this set. S, if I take alpha 1, alpha 2, etc., alpha n, okay, it should be linearly independent set, and it should be a spanning set. Okay, spanning set means, once again, we know that any vector in V, it should be expressed as a linear combination of the vectors in S. Okay, you can see this definition too. Of course, the definition one is also having the same meaning. So you can see this definition: a set S is equal to alpha 1, alpha 2, etc., alpha n is the basis of V if it has following properties. Okay, so first of all, there should be linearly independent. Okay, S must be a linearly independent set, and then S is a spanning set. So one example we had given for basis. So one thing is that it can be easily seen that, suppose I take a vector e1 is 1 0 0 etc 0, and then e2 we take 0 1 0 0 etc en can be taken as 0 0 etc 1. Okay, so this is a standard basis vector in Rn. So these vectors are linearly independent, right? We had checked earlier. So these vectors are linearly independent. So because you see that this combination C1 E1 plus C2 E2 plus etc plus Cn En equal to 0. So from this I just multiply everything. Then finally we entered with C1 comma C2 etc Cn equal to 0 comma 0 comma 0. So we are having C1 equal to 0, C2 equal to 0 etc Cn are 0. So therefore it is linearly independent. And next we want to show that this set is spanning set. This is what we had discussed yesterday. So we take a vector something like this: a1, a2, etc., an. Okay, a1, a1, a2, etc., an. So this should be expressed as linear combination of the vectors. So that is fine, because a1 you take out, it can be expressed as 1 0 0 0 etc 0. Only that first term is a1, so then you will have 1 here. Similarly, the second term you will have 1, and rest of the entries are 0, and then etc. Similarly, you have the last entry would be 1, and the rest of the entries are 0. So that you will get this vector a1, a2, etc., an. So now this is nothing but what? A1 E1 plus A2 E2 etc. plus AN EN. So therefore E1 E2 etc. EN is a basis for V, because it is a spanning set as well as it is linearly independent. Okay, and we discuss some of the results. And then this result we just have written as a corollary. So if V is a finite dimension vector space, of course, this dimension, this corollary actually leads to define a dimension. So finite dimension means you have the number of elements is counted, okay, in that basis. So then any two bases of V have the same number of elements. So that is what I have given some examples. So if you take S1 and S2 are two bases. Okay, S1 and S2 if you take as a two bases, then it should be having the same set of elements. That's what I said. Same number of elements, not same set of elements. So because this can be alpha 1 can be something. Okay, 1 0 0. Let's say 0 1 0. This is 0 0 1, and it can be 1 comma 1 comma 1, and then it can be 2 comma 2 comma 2, and it can be 3 comma 3 comma 3, something like that. So, but only thing is that this should be a basis. S1 and S2 both must be basis. If these two are basis, then the number of elements is 1, 2, and 3. And then here also 1, 2, and 3. Entries are different. That's not an issue. And I told you that we are going to focus only on this finite dimensional vector spaces, because infinite dimension is completely different subject. So we are not going to get into that. So we'll be focusing on finite dimension. Okay, so next we have defined this dimension. The number of elements in a basis of V is called the dimension of V, and it is denoted by dimension of V. Okay, so this example we had given. So specifically, we'll take three vectors and then we can just give a conclusion on this. Okay, we can give some three vectors we can take. Suppose you take SS, that usual vector will take 1 comma 1, okay, 1 comma 0 comma 0, we'll take three vectors. So 0 comma 1 comma 0, and then 0 comma 0 comma 1. Okay, so 1 comma 0 comma 0. So to be specific, okay, specifically just we'll just see that. Okay, 0 comma 0 comma 1, we'll take this. And this is first thing is that this S is linear independent. S is linear independent because none of them are dependent to each other. Okay, S is linear independent, and S is a spanning set also, right? S is a spanning set. One observation is that S is linear independent and S is a spanning set. Spanning set, because if you take A, B, C, that's what we had seen earlier. Same thing in R, and we have seen. Suppose you take A, B, C is in R3. This is a vector space. The ABC can be expressed as ABC can be expressed as A times of 1 comma 0 comma 0 plus B times of 0 comma 1 comma 0 plus C times of 0 comma 0 comma 1. Okay, so therefore this is nothing but you can say that A times of E1 plus B times of E2 plus C times of E3. So therefore ABC is a linear combination of the vectors. So maybe in words if we say that ABC is the linear combination of the vectors in S. Okay, ABC is the linear combination of the vectors in S. So therefore, S is a basis. Okay, so therefore S is a basis 1 comma 0 comma 0, and then 0 comma 1 comma 0, and then 0 comma 0 comma 1. Okay, it's a basis. So S is a basis. S is a basis. So the number of elements in S are vectors. Number of elements or number of vectors are vectors in S equal to 3. So therefore the dimension of vector space is. See, there are some results to verify that. Maybe I'll discuss in the next class. We'll do some more problems. Suppose V is in R3. So easiest way is that suppose V are R3 vector space is in R3, and also you have a subset. We have a subset is also having a three elements only, something like this. Okay, we have E1 and then E2 and then E3. Let's say this. So one you know three vectors are linearly independent. That is sufficient. But in case of this three, because here is nothing but this dimension is something different because it is an R3. Here also we are having three vectors. If it is linearly dependent, then we can't say anything about the dimension. But if it is a linearly independent, then we can say that combination. We just conclude that it is having a number of elements is 3, so we can directly conclude. Suppose if this is not R3, but if you having R2 here, but S is nothing but you have a three vectors like this 1 comma 0 and then 0 comma 1 and then 1 comma 1, something like this. So in the basis you have a three trees 1 2 3, but then in that case it can have a dependent or it can have something like that, so you cannot conclude from that. So if it is only three entries are there, and it is if it v equal to R3, then one can have a conclusion that if it is an independent vectors, then the dimension must be 3. That we can have a conclusion. So we can have this. We'll just state this result. Of course, we don't prove this result. So we can generalize this as a result. Okay, we can generalize the above this one, this discussion as a result. Okay, if V is a subspace of a finite dimensional vector space V, sorry, if W is a subspace of V equal to finite dimension. Simple language we'll write. We don't write just like that what is given in the book. Okay, so if V is a subspace of a finite dimensional vector space V, so I am writing V is nothing but a finite dimension V. Then one can say that every linearly independent, every linearly independent every linearly independent every linearly independent subset of W, every linearly independent subset of W is finite, and and it is a part of basis for W. See, W is a proper subspace. Just will give a overview of this. W is a subspace of a vector space V, but V is having a dimension, finite dimension. So dimension is finite. Let us give some finite dimension. Let's say let us assume that it has a dimension 5. Okay, V equal to, dimension of V equal to 5. Okay, so we are assuming that dimension of V equal to 5. But W is what? W is a subspace. So subspace means it can have a 4 elements. So V is having a 5 elements. So let us say that, let's say E1, E2, E3, E4, and then E5. But it is a subspace, so it can have a less than that, or it can be equal also. So we'll take 4 elements: E1, E2, E3, E4. If it is a proper subspace, then it should be less than 5. It is a subspace means you can even take a 5 vectors also. That is not an issue. But what is the theorem says? If W is a subspace of V is any finite dimension, every linearly independent subset of W is finite. Of course, if you take 3 vectors like this, subset of this, if you are choosing the vectors, all these vectors must be independent, then it is a basis. That is what we had seen this earlier case also. Okay, but we are generalizing in more general form. Okay, if W is a proper subspace of V and every linearly independent subset of W is finite, if it is finite, then it will form a basis. Okay, or it is a part of a basis. So suppose I choose W1 is subset of W. So W1 is a subset of W1. I choose as a 3 vectors only: E1, E2, E3. Or you can choose another subset. W2 also you can choose. W2 is also in W, but W2 also I am choosing in such a way that E1, E3, E4. I'm not choosing E2. But let us assume that all these vectors may be linearly independent vectors. So if these are true, then one can say that, okay, one can say that whatever this one you choose W1, it is a basis for W. And similarly, whatever you choose W2, okay, these vectors are linear independent. Then you can say that it is a basis for W2. Then one can have a dimension for your this one W also. So that is the meaning of that. If W is a subspace of any finite dimensional vector space, every linearly independent subset of W is finite, which will form a basis. This result may be useful, dealing, solving. Let us look at this some examples after finishing this theorem. Now we are going to let W1 and W2. Am I audible?
Yes, sir.
Yes, sir.
Yes, sir, you are audible.
Okay, 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 okay. Thank you. Okay, so we'll choose two subspaces, W1 and W2. Okay, those two subspaces are finite, finite dimension. Okay, W and W2 we choose, and be finite dimensional subspaces. W and W2 be some finite dimensional subspaces of a vector space V of a vector space V. Okay, let W and W2 be finite dimensional subspaces of vector space V such that W1 intersection W2 is finite. Sorry, W1 intersection W2 is of W1 plus W2 will be same as dimension of W1 plus dimension of W2. Okay, dimension of W1 plus W2 will be same as dimension of W1 plus dimension of W2. So let us give something like that. Okay, maybe it may not be exact the geometric way of representation, but anyway, let us to understand to be more specific. Let me say this is a vector space. Okay, and I am choosing two subspaces. Let us say this is my W1 and this is my W2, and then W1 intersection W2 is only one thing, one vector is there. Maybe you can join these two, so only that will be a with the condition that W1 intersection W2 is just zero. Only one entry is there, that is zero only. So maybe the intersection is there, but only one entry is there, zero. Intersection is non-empty, something different meaning. But here the vectors, W1 intersection W2 is zero. That means one vector is there. Zero is a vector. Okay, W1 intersection W2 is zero is there. Then the dimension of these two will be same as separately dimension of W1 plus will be same as dimension of W1 plus W2. If you add these two subspaces, then that would be the dimension of that. So we can choose something like that, right? W1 and W2 will choose a subspace. Let us choose W1 is a subspace. Let's say 100. Okay, why to take always in R3? We'll take in R2 also. Let's say 1001, and similarly W2 1 comma 1. Let's say 2 comma 3, something like that. Okay, so we have chosen two subspaces of a vector space V. Let us say these two of a vector space V. Okay, and then let us also we whenever we speak about dimension is connected to basis, because the dimension of something is nothing but the number of elements in the basis. Let us say that this forms a basis, and similarly this forms a basis. Plus W2 will be what? W1 plus W2. Okay, dimension of W1 I am saying as 2, because it forms a basis, let us assume. Of course, it is a basis because 1001 is a basis. So dimension of W1 is 2. And then we also assume that dimension of W2 is also 2, because there are number of elements in the entry is 2. So this is same as dimension of W1 plus dimension of W2 will be 2 plus 2 is 4. We can always construct an example like that. So that is what I would like to say. It's not that exactly these entries are true. Just I want to give a counter example. We can always try to see that, and which will be same as the dimension of W1 plus W2. So if you consider addition of these two vectors W1 W2, then the dimension will be we should get 4. That is what the theorem says. Okay, that is what we want to do it. So we remember what we want to prove, that we want to prove this two will be same as dimension of W1 plus dimension of W2. What we do that we'll assume one side. Okay, one side we'll assume that. Why we want to assume that W1 and W2 are finite dimensional subspaces. Okay, so if it is a finite dimensional subspaces, so therefore the number of elements is fixed. That means that is a finite. The number of elements in W1 is finite, and similarly the number of elements in the W2 is finite, because W1 and W2 are finite dimensional subspaces. So the first line we can write, since W1 and W2 are finite dimensional, so we can have, so we can have we can have let us choose two vectors, beta 1 and beta 2. Beta 1 we choose as a vector alpha 1, alpha 2, etc., alpha m. And then beta 2 we choose, okay, beta 1, beta 2, etc., beta n. Acha, why you want to be beta? Let us put some other notation here also, because inside also we are considering one beta only. So let us say this is A and this is B. So what I want to say that, okay, W1 and W2 are finite dimensional. Therefore, I can consider two bases, alpha 1 to alpha m, and then beta is a basis for W1, and this is a basis for W2. Okay, the first one is a basis for W1, and the second one is. So if it is a basis, then I can say that dimension of W1 is m, and then dimension of W2 is n, because you see here I'm considering till m vectors. There are m elements, and here I'm considering fixing n. There are n vectors. These two are finite, so I can fix any number. Okay, so I'm just fixing the first one is m, and second one is n. So there are m entries in W1, and there are n entries in W2. So therefore, dimension of W1 is m, and W2 is n. Now, okay, this is true because W1 W2 are finite dimensional. Now, what we want to claim? Now we want to claim dimension of plus W2 is same as dimension of W1 plus dimension of W2. But this is we have done. This is what we want to prove. Okay, this is what we want to prove. Dimension of W1. So that is what we have to prove. Okay, because these two are we have done. Dimension of W1 is m, and W2 is n. Those two are true. Okay. Now we have to only just do this part only. Dimension of W1 plus W2 is m plus n. Now we'll do that. So if I want to show that dimension of W1 plus W2 is m plus n, what I show that elements. Okay, so there are bases which has m plus n elements. So you can say the number of elements in the basis is called the dimension. So now what I have to show that. So I have to show that we have to show that okay, alpha 1, alpha 2, etc., alpha m, and beta 1, beta 2, etc., beta n is a basis for W1 plus W2. Okay, so we have to show that alpha 1, alpha 2, etc., alpha m, and then beta 1, beta 2, etc., beta n. It is a basis for W1 plus W2. So it is a basis. Now we want to prove that it is a basis. Again, two things. One is that let us consider this notation. This as some B prime. Okay, this is we'll consider as a B prime. We have to show that B prime is linearly independent, and we have to show that B prime is a spanning set. Two things. Okay, so two things we have to show that we have done. Okay, we are done. So these two things we have to show. Okay, then we'll see that. B first we'll try to show that B prime is linearly independent, and then we'll come to the basis. Okay, so we show that the first one we show that is linearly. Consider the linear combination C1 alpha 1 plus C2 alpha 2 plus etc. Cm alpha m plus, let us put something notation, D1 beta 1 D2 beta 2 plus etc. Dn beta n equal to 0. Okay, now all this C1 C2 etc. C and then D1 D2 etc. Dn are scalars. Okay, so now what I know that one thing I know, what I know, first this alpha 1 to alpha m, these are vectors in W1. Okay, and then beta 1 to beta m, these are the vectors in W2, and this, their union is vectors in B prime. Okay, so we know that alpha 1 alpha 2 etc. alpha m, it is a basis for W1, and we know that beta 1 beta 2 etc. beta n, it is a basis for W2, so that is okay. So I can say this combination u plus v equal to 0. Okay, where u is equal to that, where you can write specifically if you want. Okay, I'm just writing this as u and this another, this as v, u plus v equal to 0, and then provided that I'm saying that u belongs to w1 and then v belongs to w2, because u is nothing but c1 alpha 1 c2 alpha 2 etc. cm alpha m, whereas alpha 1 alpha 2 etc. alpha m are the vectors in w1. Similarly, beta 1 beta 2 etc. beta n are the vectors in w2. So I'm saying u plus v equal to 0 means u belongs to w1 and then v belongs to w2. Am I audible?
Yes, sir.
Okay. So one quick observation. So u plus v equal to 0 means what? I can say that u is equal to minus v. U plus v equal to 0, and we are considering. So u equal to minus v. But what we know already, u is in w1. But v is nothing but this one, this combination, but which is in w2. V is in w2 means minus v is also in w2 only. Okay. So therefore u belongs to w2 also. U is equal to minus v, since v is in w2, so therefore the minus is nothing but a scalar here. Okay, scalar times of something which is again in w2, so therefore u should belongs to w1 intersection w2. So otherwise also we can write v equal to minus u also you can write, so the both will be w1 intersection w2. That is, once again you can prove it, that is not an issue. Similar analysis you can do, but what we have given that w1 intersection w2 is 0. Okay, that is what we are given. So which implies that u equal to 0. So u equal to 0 means u is equal to minus v. So v is also 0. It implies that v is also 0. So u and v are 0 now. So u and v are 0 means what? U equal to 0 implies that what? U is nothing but c1 alpha 1 plus c2 alpha 2 plus etc. cm alpha m equal to 0. But since alpha 1, alpha 2, etc. alpha m is a basis for w1, so which implies that it is linearly independent set. It is a linearly independent set. Similar analysis, v equal to 0 implies that what? You will get d1 beta 1 plus etc. plus dn beta n equal to 0. So from this you can say that beta 1 etc. beta n are linearly independent. Similarly, you can say that is are linearly independent. Okay, so therefore it is a linearly independent means what you can say that all these scalars are 0. C1 equal to 0, C2 is equal to 0, etc. Cm equal to 0. Similarly, D1 equal to 0, D2 is equal to 0, etc. Dn equal to 0. So therefore, B prime, the set B prime is linearly independent. Okay. Simple analysis. It may look something complicated, but it's not complicated. Very simple. Okay. So the other thing, okay, we have shown that now it is a linearly dependent. Okay, B prime is linearly dependent. Now second set, what you have to show that B prime is spanning set. The second thing we have to show that B prime is spanning set. Okay. So spanning set means, okay, to be very specific, what you want to show that, let you have to take a vector z is in w1 plus w2. Z is in w1. So then y is in w2 such that z can be expressed as x plus y, because z belongs to w1 intersection w1 plus w2. So z should be expressed as w1 plus the vectors in w2. So that, but what we know for w1 w2 are bases. Okay, so you don't need, so w and w2 are bases, so it will have a linear combination. Okay, so what we are assuming that x belongs to w1, which implies that x can be expressed as linear combination of the vectors in w1. So c1 alpha 1, c2 alpha 2 plus cm alpha m, because alpha 1 alpha 2 etc alpha m are in w1. Okay, so any vector if you take, that can be expressed as linear combination of the vectors. Similarly, if you take y belongs to w2, similarly if you take y belongs to w2, y is equal to, I can write d1 beta 1, okay, d1 beta 1 plus d2 beta 2 etc dn beta n. Okay, now we'll see that z equaled, now z equaled x plus y, which is nothing but what, addition of these two. So this is nothing but c1 alpha 1, c2 alpha 2 plus etc cm alpha m plus d1 beta 1, d2 beta 2 plus etc dn beta n. So now z is nothing but, z is a vector, z we have taken w1 plus w2, but it can be expressed as linear combination of the vectors in w1 plus w2. So therefore it is a spanning set. B prime is a spanning set. So therefore B prime is a basis. So B prime is what? Now the B prime will be alpha 1 to alpha m, and then beta 1 to beta n. So it is a basis means dimension of B prime. B prime we have chosen as w1 plus w, w1 plus, there are n vectors. So this is, therefore we can conclude that dimension of w1 plus dimension of w2 will be same as dimension of w1 plus w2 if provided this condition, w1 intersection w2 is 0. Okay, if you choose w1 intersection w2 is 0, then it should be something like this: dimension of w1 plus w2 is same as dimension of w1 plus dimension of w2. Okay, so this is the proof. So now we can write a more general form of this theorem. So because we are now imposing this condition that dimension w1 intersection w2 is 0, we are imposing. Suppose we assume that without that condition, okay, dimension of w1 plus w2, we don't assume that that should be 0, then you'll be having dimension of w1 intersection w2 also, that is also there. Okay, So therefore, that is nothing but the more general form of this theorem is nothing but. So that we are going to discuss dimension of W1 plus W2. This is over. Dimension of W1 plus W2 plus the dimension of W1 intersection W2 is same as dimension of W1 plus dimension of W2. So this is quite interesting because see, we are not using the condition on 0. Now we don't impose any condition on 0, any condition we don't assume, and we directly prove that now the dimension of W1 plus dimension of W2 will be same as dimension of W1 plus W2 plus the dimension of W1 intersection W2. Okay, so this will be no, we'll be giving a proof of this tomorrow. So anything you would like to ask today?